Photonic chips are microchips that use light instead of electricity to process and transmit information. Instead of moving electrons through metal wires like traditional semiconductor chips, they guide photons, particles of light, through tiny optical pathways built into the chip. At a basic level, a photonic chip contains components such as waveguides, modulators, lasers, and detectors. Waveguides act like roads for light, directing it across the chip. Modulators encode data onto light signals by changing properties like intensity or phase. Detectors convert light back into electrical signals when needed. All of this is fabricated on a very small scale, often using materials like silicon, similar to conventional chips. The main advantage of using light is speed and efficiency. Light can carry data much faster than electrical signals and can travel longer distances without losing strength. It also generates much less heat, which is a major limitation in today's electronic processors. As computing systems become more powerful, managing heat and energy consumption becomes increasingly difficult. Photonic chips address both of these challenges at once. Another key benefit is bandwidth. A single optical channel can carry multiple data streams at different wavelengths, a technique known as wavelength division multiplexing. This means one pathway can handle far more data than a traditional electrical connection. In data centers, where massive amounts of information are constantly moving between servers, this makes a significant difference. Photonic chips are already being used in certain areas. Optical transceivers in data centers rely on photonic technology to move data between racks and servers. Fiber optic communication systems also depend on similar principles, though those are typically larger-scale implementations rather than integrated chips. More recently, photonic chips are being explored for artificial intelligence and high-performance computing. Training AI models requires moving huge volumes of data between memory and processors. Electronic interconnects can become a bottleneck. Photonic interconnects can reduce this limitation by allowing faster and more efficient data transfer. Some companies are also experimenting with fully optical computing elements, where certain calculations are performed directly using light. Despite the advantages, there are still challenges. Integrating photonic components with existing electronic systems is complex. Light behaves differently than electricity, so designing compact and precise optical circuits requires specialized engineering. Manufacturing is also more difficult, especially when trying to combine lasers and detectors onto the same silicon platform. Another limitation is that photonic chips are not yet a complete replacement for electronic chips. Electronics are still better suited for logic operations and general-purpose computing. Photonics is currently most effective for communication and data transfer, although research is ongoing to expand its role. Materials also play an important role. Silicon photonics is widely used because it can leverage existing semiconductor manufacturing processes. However, silicon is not ideal for generating light, so other materials like indium phosphide are often integrated for lasers. This adds complexity to the production process. Looking ahead, photonic chips are expected to become more common as demand for faster and more efficient computing grows. They are particularly relevant in areas like cloud computing, telecommunications, quantum computing, and advanced sensing systems. In simple terms, photonic chips are not about replacing electronics entirely. They are about solving specific limitations where electricity struggles mainly speed, heat, and data transfer. As systems continue to scale, combining electronic and photonic technologies is likely to be the most practical approach.